So now we're gonna have a talk given by Lino Grama from Unicamp. So thank you, Lino, for being here with us. Lino will speak on scalar curvatures of invariant almost Hermitian structures on generalized flag manifolds. So feel free to start, Lino.
Okay, thank you, Eder, and thank you all the organizers for this amazing conference. It's very nice to see a lot of friends virtually, but and I hope everyone is safe and okay. Let's start to share my screen. Okay. This is a joint work with my friend Ailton Oliveira in University of Mato Grosso do Sul, State University of Mato Grosso do Sul. Okay, and I just report some progress in this project. I will avoid some details because that's just a short time, but I can discuss if people have some interest in this. I will start to recall some basic concepts and definitions. Probably these concepts appear in the previous talks, and I just pass this very quickly. And we start with an almost Hermitian manifold with the real dimension 2n, and the J is an almost complex structure, orthogonal with respect to the Riemannian metric G. Okay, this part. We defined the fundamental two form or Keller form. I denote this by F, and this is given by the J of G, X, and Y. Okay, this is exactly the two form is symmetric because the G square is -1. It's a very canonical. And we have a remarkable pair here. It's when J is integrable. In this case, this manifold is a complex manifold. Okay, the change of charge is allomorphic, given by allomorphic functions. Okay, and this fundamental two form is closed. Okay, this is a very distinguished pair, and of course, and no, we need to decide if the manifold can have this pair or not. And in this case, we call this a Keller structure, OM. Okay. And we have a classification of the almost Hermitian structures OM. This is provided by Greyer-Vela, and they classify the almost Hermitian, the all pairs, into 16 classes. Okay, and the key point here is analyze the symmetries of the covariant derivative of the two form, the fundamental two form, where D is the Levi-Civita connection of this Riemannian metric G. Okay, and this is will be important in our situation here. And given a linear connection, we call this nabla, the linear connection Hermitian, if it preserves the almost complex structure and the Riemannian metric. But it is important we not assuming that J is integrable here. Okay? And this is a definition. Given an almost Hermitian manifold, that is a unique connection that satisfies. This is a Hermitian connection, and the one part of its torsion vanish. Okay, this is called shared connection or canonical connection. if J is actually integrable, is a complex structure, this connection is a connection compatible with the holomorphic structure of the holomorphic bundle, holomorphic tangent bundle. Okay, but in this case, we're not assuming the J is integrable, but we still call this a Chern connection. People also call canonical connection. Okay, but this is important. This is in general, it's not the Levi-Civita connection. Okay, this is very important. It is the connection can be torsion, to have torsion. And given a linear connection, you can define the curvatures, the curvatures tensors, etc. Okay, each tensor scalar curvature for the associated connection. And we call the Chern scalar curvature, we denote by SC, is the scalar curvature of the Chern connection. And given by this usual, the sum of the symbol, the index, ij, and the R is the curvature tensor associated to the Chern connection. We have the unitary frame. This is the usual notation. U I bar is a J U I. Okay. And if this almost Hermitian manifold is a Keller manifold, in this case, the Chern connection coincides with the Levi-Civita connection. Okay? And in this case, we have the Riemannian scalar curvature is equal to 2 times the Chern scalar curvature. Okay. And okay, in general, what is the meaning of the Chern scalar curvature in the context with there's no Keller manifold? In general, it's very hard to find this meaning. But if you look for almost Hermitian manifolds that satisfies this equation, okay, you can have some geometric meaning for this. What means this scalar curvature? Okay, the Chern scalar curvature. And then we have the following definition. These appear in the literature are one pair J here, GJ. We call this Keller-like scalar curvature metric if satisfies this equation. Okay. Right? This is we found that this is a KLSC metric. This is we found it recently in this concept, this name. Okay, this is in the Dabrowski lock. Okay, but this is just the metric that satisfies this equation. Okay? This let's see some examples. If you have a nearly Keller manifold, okay, this is very well studied class of almost Hermitian manifold. And the nearly Keller manifold and the almost Keller manifold, if this structure satisfies this equation, they are necessarily Keller. They are Keller metric. Okay? This is very recent by Ligemi Upmeyer, Apostolov, Dragis, in 2020. If the pair belongs to this gray Ervella class, okay, and satisfies this equation, then again the pi is scalar. Okay? And this is also very recent results. And if you have compact Hermitian, this is important. In this case, the complex structure is integrable. Okay? And you have the metric satisfies this equation, if and only if the metric is scalar. Okay. This is a go back to the Gauduchon. Gauduchon studied a lot of these curvature properties of the linear connection with torsion, etc. And the Liu Yang in 2014. Okay, and this way you can think maybe this is a is a process to find Kähler metrics, because to solve this for a general setup, this is an equation involving curvatures, and this will lead naturally to differential equations in the manifold. Okay, this is an equation involving curvatures. Okay, and the natural question here is, can we provide examples of almost Hermitian non-Kähler manifolds that satisfies this equation? Okay, because if you have a Hermitian manifold, Hermitian manifold will be Kähler, and for some Greyer-Vela class, if this input this constraint, this forces the pair to be Kähler. Okay, right. Okay, and this is the goal of our project here. We make a study of this. We study this question for a class of in the generalized complex generalized flag manifolds. Okay, and we keep this manifold, this homogeneous space, with the invariant almost Hermitian structure. Okay, and this is done in several situations, like for instance, Einstein metric, scalar Einstein metric. This is a differential equation, and when you put this in some invariant context in the homogeneous space, you can simplify the situation. Simplify it's a quotation marks, because this is very hard, but we can work here with the Lie algebras, Lie groups, representation theory, etc. Okay. Okay. Oops, sorry. Okay, and we have an advantage here, because for full flag manifolds, we have a complete classification of the invariant almost Hermitian structures given by the Saint-Martin-Negre in 2003, and Saint-Martin and Rita de Jesus also provide a lot of partial results in generalized flag manifolds in general, in the partial flag manifold. And this is very useful. So mainly the formalism introduced by Saint-Martin-Negre to how to deal with this invariant pair. Okay. Here, just put some concept here. What is the flag manifolds? Just I suppose these are unnecessary for this audience, but just for fix the notation. Okay, we start with the complex simple Lie group. We fix a parabolic subgroup. We denote by G. Okay, GC is the complex. Just G is the maximal compact subgroup, and the K is this intersection, the parabolic and the compact Lie group. And the generalized flag manifold is this homogeneous space. We have this is a diffeomorphism or biolomorphism, and we have these two descriptions. Okay, and of course we have a complex structure here comes from the complex Lie group, and this is a compact homogeneous space. This is very easy to see this side, and this is complex. Okay. Okay, if you pick the parabolic subgroup to be the Borel subgroup, in this case we have this intersection is the maximal torus, and this homogeneous space is called a full flag manifold or maximal flag manifolds. Okay, flag manifolds is a reductive homogeneous space. That is, we have this decomposition, very well known, and that satisfies this. Invariant by the M is invariant by isotropy group K, and one can identify this tangent space of the origin with M. And this O is the trivial constant. Okay. Let me put some, just recall some facts. There is a one-one correspondence between the G-invariant tensors on the homogeneous space and tensors on this vector space that are invariant by the adjunct representation here. So the isotropic group. In this case of the complex manifold, of complex flag manifold, sorry, the isotropic representation decompose into irreducible and no equivalent piece. Okay, this will be important. And a description of the invariant matrix in this setup, it just are positive numbers, okay? Where this R is the number of the isotopic components. Okay? These probably this notation appear here in the previous talk, maybe for the people working the Riemann geometry in homogeneous space. Okay? And in a similar way, we can give the description of the invariant almost complex structure. But now this is a R upper here is a R signs plus or minus 1. Okay, where this R is the same number of the isotopic components. These are very similar to Riemann metric, but now you give it just by signs, minus plus 1 or minus 1. Okay. Just let's try to explain this, just put more clear, just in case of the full flag manifold. Because for the Riemann metric, disappeared before, I just skip. But for the complex, almost complex structure, maybe just take 2 minutes here to put this. Again, this is a very canonical for this. We just fix the root space decomposition of the complex Lie algebra, the simple Lie algebra. Okay, we have the Cartan sub algebra 8. We denote by capital pi the set of the roots with respect to this pair, where we have this decomposition. And we denote, okay, this G alpha is the one-dimensional complex root space. We fix a veil base of the GC. Okay, this is a distinguished element in each one-dimensional G alpha space, one-dimensional space. This satisfies this property with the. Oh, sorry, this guy, this bracket here is the Cartan killing of the complex Lie algebra, Cartan killing 4. Okay, and now using the root space decomposition, we can give a base for the compact real Lie algebra. Okay, the base of the compact real Lie algebra will be spanned over R, the real numbers. This is the realification of the Cartan sub algebra multiplied by the imaginary unity, A alpha and F alpha, where alpha runs in the capital pi, where this is the A alpha is given by this vector, and the S alpha is given by this vector. Okay, just put this in more clear. If you take, for instance, SU3, this part will be the diagonal matrix with purely imaginary parts in that diagonal. Okay, and this guy, for instance, will be the matrix if you put 1 in the ij position and minus 1 in ji position. Okay, and this part will put some I in ij position and I in Ji position. Okay, this is just to put this in more concrete. Okay, but this is and okay, we define this two-dimensional real space. Okay, this and for full flag manifolds, the tangent space we give this decomposition, and each of this U alpha is a isotropy component of the isotropy representation. Okay, and now we define the almost complex structure by this expression, and recall this X alpha is the veil base. Okay, and we plug this with the expression of the A alpha and S alpha. Okay, and you make some computations you arrive. This is U alpha is invariant by J, and the J square is a minus identity, and this is just the rotation 90 degrees or minus 90 degrees. Okay, this take A alpha and gives S alpha, and S alpha minus A alpha, or the opposite depends on the sign. Is a plus or minus 1. This is a plus 90 degree or minus 90 degree. It's a rotation. It's a very okay. It's a usual and more concrete. In this flag manifold, this is a six-dimensional real homogeneous space. If you pick this invariant metric and this almost complex structure, this in fact is a complex structure, it's integrable, and this pair is scalar. Okay. Or if you pick this 1, 1, 1, this is called the normal metric. This comes from the Cartan-Killing of the compact group. And you put these signs, the choose of signs. In fact, this pair is nearly scalar. This satisfies this equation. Okay. And for these flag manifolds, we have just these two invariant almost complex structures, up to conjugation and equivalence. Okay, there's one integrable and then another no integrable. Okay, and now we state our results to finish. Okay, okay, this is just for this is the first result. Just joint with the Hilton Oliveira. We start with this flag manifold. And we have one invariant almost Hermitian structure, okay, where this metric is parameterized by the triple of positive numbers x, y, z. Okay, this is we denote the Chern scalar curvature, and S is just the Riemannian scalar curvature, and we have the solution for this equation if and only if. First, the pair belongs to this Gray-Arrela class, where this is no integrable, the J is no integrable, and the metric satisfies one of the following relations. They will have some equation here. Okay, this is not for this is a solution of the problem. Okay, or this solution. Okay, in this case, we provide the example of this situation. Okay. Or if you belong to this class, where this is integrable. But in this case, if it is integrable, okay, make the computation, arrive at this metric which satisfies this relation. It is in fact scalar. This is a scalar condition for this triple to be scalar. Okay. In this case, we detect scalar metrics by this procedure. Okay. Just to remark, if you take this three equal numbers, this belongs to the W1 Gray-Arrela class. This is an Illy scalar, and there's no solution to this. Okay, we need to take the Hermitian structures belonging to the two components. Okay. We have the similar result for CP3, but this is not symmetric CP3. This is like manifolds is the same game, but now there's the invariant metrics depend on two parameters. Okay, And we have also two invariant almost complex structure, one integrable and another no integrable, up to equivalence and so on, etc. And then we have this, the pair belongs to this class. And then we have this equation, this line. Or the J is integrable. In this case, we have this, oops, sorry. This is wrong. Y is a 2x. Okay, this is a Keller mass. In fact, it's a Keller item. Okay. And then again, if you pick these two equal numbers, these are nearly Keller, there's no solution. Okay, the previous two example is 6-dimensional. By now, we put some high dimension, and then we consider this guy. But this guy there's a lot of components. It's not easy to analyze. But we look at this high, like the total space of this vibration. We also analyze these homogeneous spaces G2 over the maximal flag of G2, and then we look at this. I like this total space of this vibration, and then we just analyze a family, one parameter of family of metrics. These are given by the rescaling the metrics in direction of the fiber by the factor x squared. Okay, this is called a canonical variation. Okay, and for this family, in the case of the SU4 over T3, this has a 4 invariant almost complex structure up to equivalence. And the metric given by 6 parameters. But this we keep the 1 in the base. This is the normal metric. And the rescaling the metrics on the fiber. This is they have 3 parameters, but the same number. Okay. And we have this table for each of the invariant almost complex structure. For instance, for this, we have the belongs to the Greyer-Vela class W3 for all x, and there is no solution. But for G2, J2, we have W1 plus W3 for all x. Just for this number, we have the solution. Okay, so on. But here is the difference for x equal to 1. For x equal to 1, we have the normal metric. Okay, this all parameter is 1. And this belongs to this Greyer-Vela class, there is no solution. But for all x differential of 1, we have one solution. Okay, sorry. If x is different for 1, we have one solution at this point, or 2 solutions at this point. Okay. And for G2 over maximal torus, you have 32 invariant almost complex structure. You have for this Ji, where R is one of this number, we have no solution. And for the others, for the normal metric at time 1, there is no solution. If for x not equal to 1, we have at least one solution. Okay. Just to put some, this is the table. Okay, this is a little bit more complicated, but this encodes a lot of the structure of the proof. Okay, we use the formalism of San Martin gradus here. We actually compute the derivative of the fundamental form in the split in the 4 pieces, and the pieces analyzed piece by piece. Okay, and here we have the solution of the problem. Okay, my time is over. That's it. Thank you.
Okay, thank you. Let's thank Lino again. So, questions and comments?
Yeah, Lino. Hi, how are you? So, if you ask for the Ricci tensors to be equal, to coincide for the 2 connections, is that too strong? That's imply Kähler?
Oh, we need to think about, okay, because this I guess there's some constraints, but maybe it's too strong. But I need to check a little bit more. Okay.
And what about?
I understand your question. I understand, but
yeah, but in your examples, for instance, in the SU3 over T,
okay.
have you checked the Ricci tensors? In part 1, for instance, in the first theorem.
I see.
I see. Have you checked if the Ricci tensors are the same?
The J Ricci tensor, right? The Ricci tensor associated to the almost complex structure.
To right? The Chern and the Ricci tensor associated to Levi-Civita. These two Ricci tensors.
I see. No.
Okay.
No, because this that is a recent analysis from how to provide the scalar curvature, just analyzing the pieces of the derivative of the covariant derivative of the Keller form. Okay, and we needed to work out a little bit more because the main thing is how to write this. Okay, I understand. Maybe for one example we can work out, but for general picture. Is a little bit more complicated, but we are. This is a more big project. So we are analyzing more stuff here.
And what about these tables at the end? Can you show them again? Did you
the white or the green? The white paper or green paper?
The tables. The tables at the end. Did you get almost scalar examples with the same?
No. Just W. I don't remember the table or the names. But,
no. The table you show in the table, the DF0. Did you get any example with DF0? Almost scalar.
We have two DF minus and DF plus. Okay. We have two DF here. Okay, we have just 4 pieces. I have not the time to
but isn't F the 2 form?
Yeah, this is the 2-1 part. Okay, minus this is a 1-2 part of the DF.
Okay. So both has to be 0 to get almost scalar.
Exactly.
And did you get any example of that?
Okay, let me check. Oops. No. At same time, no. But this is just for the G2. Okay.
Okay.
But
okay. Okay. Thank you.
Okay.
So more questions or comments? Right, so let's thank Lino again.